This video is meant to introduce you the Multi-Dataflow Composer tool, which is a software framework for the design and deployment of coarse-grained reconfigurable substrates and accelerators. It is the first of 3 videos, where you will learn about the background, the reference technologies and the applicability of MDC. MDC is the result of the joint effort of the University of
Sassari
and the University of
Cagliari. Francesca Palumbo
is assistant professor at the University of
Sassari
and
Claudio Rubattu
is doing a joint PhD.
Claudio Rubattu
Is co-supervised by
Francesca Palumbo
and
Maxime Pelka,
at the
Institut national des sciences appliquées de Rennes.
The group of the University of
Cagliari
is composed by
Luigi Raffo,
who is a full professor in electronics,
Carlo Sau,
an assistant professor, and
Tiziana Fanni,
who is currently a postdoc. Embedded computing systems are, nowadays, pervasive, distributed everywhere and potentially constantly interacting with each other. Depending on the reference application scenario, they are required to meet complex functional and non-functional requirements, associated with dynamic and variable behaviors, real-time constraints and efficient system consumption. These requirements unfortunately tend normally to collide. The Multi-Dataflow Composer tool was originally conceived within the multimedia embedded systems domain, which design requires to concurrently offer high-performance real-time behaviors, flexibility over a plethora of frequently evolving standards and power awareness at the same time. To tackle those issues, we combined coarse-grained reconfigurability and dataflow models. Coarse-grained reconfiguration is exploited to optimize and accelerate in hardware a combination of different specifications. The integration of those specifications is enabled and facilitated by the adoption of the dataflow model of computation. The baseline functionality of the Multi-Dataflow Composer dates back to 2012, when the University of Cagliari started the Reconfigurable Platform Composer Tool project funded by the region of Sardinia. This project was meant to provide an automated co-design environment for reconfigurable multi-context systems, specifically aiming to reduce their time to market while guaranteeing high performance and optimization capabilities. The main outcome of the Reconfigurable Platform Composer Tool project was the first version of the Multi-Dataflow Composer. Reconfigurable architectures are considerably more flexible than standard application-specific integrated circuit, while capable of achieving better performance than general-purpose architectures. They can be classified in fine-grained and coarse-grained, and while the second ones are less flexible than fine-grained ones, being capable of switching just among a given set of functionalities, they demonstrated to be implementable on ASIC2 and require less memory to store the configuration stream that, in turn, means faster switch among configurations. The MDC tool is composed of different parts. The first one is the baseline MDC core, performing the coarse-grained system composition, meaning that different input dataflow specifications are merged into one single coarse-grained virtually reconfigurable substrate. The other elements of MDC are the structural profiler, which is responsible of exploring the entire space of implementable solutions to find the optimal substrate configuration according to given constraints. The dynamic power manager, which aims at partitioning the overall system specification to implement, at the hardware level, dedicated power-saving strategies. Finally, the coprocessor generator performs the complete dataflow to hardware customization of a Xilinx-compliant multifunctional accelerator. From the user point of view, the adoption of the MDC tool is made simple by the usage of a graphical user interface. He or she only needs to specify the input dataflow specifications to be combined, the communication protocol and the HDL component library to be adopted. Then, he or she can optionally request the execution of one of the MDC additional features, for which different tabs are provided. Now let's see where you could decide to use MDC. MDC is effective when you are dealing with applications that share operators, so that you can really benefit from a coarse-grained reconfigurable approach. Alternatively, it can be used when the same application can surf among working points, playing either with parallelism or in other cases with the depth of the computation. MDC has been assessed in the neural signal decoding field. Considering prospective implantable devices, neural signal decoding is required to be not only fast, but also implemented over a very low area and low power substrate. MDC can help building such kind of accelerator. By profiling the application, we defined its composing kernels, which are 12 overall for a total amount of actors equal to 46. MDC allows creating a reconfigurable data path that severely decreases the number of actors to be instantiated, at the expense of usage of a large number of switching elements. Nevertheless, the achieved area and power results are really promising. Recently, coarse-grained reconfigurable hardware demonstrated to be particularly energy efficient in approximate computing studies. If at the application level, you are capable of defining a trade-off among computing precision, which in turns means quality, and energy. Then, at runtime, you can try to use coarse-grained reconfiguration to switch among the different energy profiles of the system. Starting from a software approximation work of an INSA-REN research group, we defined the approximate interpolation filter of an HEVC decoder. At runtime, it is possible to choose the precision level to be executed. Looking at the curves, the achievable trade-off allowed by our tap variable coarse-grained reconfigurable filter is clear. The comparison is against the legacy 8-tap filters for Luma and Chroma of the HEVC decoder. Reconfiguration involves high resources overhead, in terms of number of lookup tables and flip-flops, as well as reduction of the maximum operating frequency. However, our approach guarantees a trade-off in terms of energy consumption and image quality. You can clearly notice from the graphs as the reconfigurable filters, which are the red lines, consume more than the non-reconfigurable ones, look at the blue lines, only when the maximum precision is selected. Going back to the tables, using a lower number of taps can guarantee a better latency or, equivalently, a higher number of interpolated pixels per execution. This consideration can be exploited tuning the frequency at runtime. The green curves in the graphs are obtained decreasing the operating frequency, keeping constant the throughput. This positively affects energy consumption, as clearly visible in the Luma case, which is on the left-hand side. Let's quickly see where we are currently adopting MDC. In 2017 we started an EUH2020 project on the development of model-based design, verification and deployment framework for cyber-physical systems named Cerbero. Cerbero is adopting the multi-dataflow composer tool to handle reconfigurability at the edge on FPGA-based platforms. In 2018 we started an ECSEL project on the integration of adaptive video processing pipelines, named FitOptimize. In FitOptimize, the multi-dataflow composer tool will be used to deploy accelerators for video content analysis and face recognition, in the context of the water supply use case. To learn more about MDC and its applications, here are some references. Please take a look to the next two videos, which will explain in details MDC baseline core and all its additional features.